Okay, thank you. So my name is Milad. I'm the technical project manager for Indra Australia Transport Department. Today I'm going to go through who Indra is, what we are doing in Australia in particular, and introduce you to Sydney Trains project as one of the large enterprise projects we've done in Australia. And I will introduce you to 3 cases which we utilize data analytics and big data to help Sydney Trains to more efficiently operate and maintain their network. So there will be 3 sections: who Indra is, Sydney Trains CCTV platform, and later on 3 case studies for visualization of data analytics and big data in operation and maintenance of Sydney Trains network. Indra, as a global company, we have 49,000 professionals all around the world. We have presence in 140 countries. And you can see here in this slide that a big portion of the revenue is spent on R&D works and projects. So in general, we are a technology company, and for most of the projects we do, we develop customized solutions for our customers. Here in Australia, we have around 150 professionals working with Indra. We have 3 offices in Sydney, Brisbane, and Taylor's Beach. We have different, we are active in different sectors. So we are majority of traffic management systems around the world, they belong to Indra. Also, we are working with the Department of Defense, transport like Sydney Trains, Transaven, and also in energy sector. To focus more on transport sector, we have more than 500 customers around the world. We have our own ticketing system. More than 20 million daily ticketing transactions are going through our system around the world. More than 8,000 kilometers of roads are controlled by Indra systems. And we, on daily basis, we control and operate 15,000 vehicles and onboard units. Plus 3,000 kilometers of high-speed rail lines around the world, they are controlled by Indra systems. In general, we are active in almost all the sections of transport industry, including the infrastructure, which includes roads, rails, airports, ports, and plus the resources like cars, trucks, buses, trains, ships, subways, and all the other kind of moving vehicles you can imagine. And we have different customers, including government, authorities, and regular bodies. Here in Australia, at the moment, we are working on 2 major projects. One is with Sydney Trains, which I will give you more information. We deployed the largest CCTV system in Australia, and actually it is one of the largest CCTV systems in the world. Also, we are implementing an IOMCS system, similar to what the previous presentation was talking about, for Transaven in Queensland. So the scope of that project is to integrate the control systems and traffic systems of 2 toll roads, 3 tunnels into 1 control system, 1 monitoring system, to help the Transaven to efficiently control everything from 1 location. And in this project also, we use data analytics and big data to, for example, forecast traffic, to make smart decisions, and control traffic systems. Maybe next year I will give you more information about this project, but mainly for this session I'm focused on Sydney Trains. Okay, so Sydney Trains CCTV project. Here you can see some pictures of
hello, can you stop 1 second? We have like some technical difficulties.
Okay. Okay, so going through the next slide, here I will give you more information about the project we've done for Sydney Trains, the CCTV system of Sydney Trains. So this system has 12,000 cameras. The scope of work for this system was to replace and upgrade the old CCTV system with the new technology using IP-based systems. And the scale of this project, this is the biggest system in Australia and one of the biggest top 3 projects in the world, using a flat architecture to connect 12,000 cameras and make it available to more than 2,000 users. So it covers 330 railway stations. So the geography of this project is vast. We have more than 1,000 active users. In general, the system is designed to be capable of servicing 2,000 users. That in the network, we have more than 50 SAN storage systems, more than 10 petabytes of SAN storage capacity for both analytics and video storage. This project, the name is CCTV, but actually the infrastructure to provide this, to deploy this CCTV system is massive. The network, the CCTV network has more than 1,000 switches, routers, layer 3, layer 2 network equipment, more than 380 compute systems, including servers, both virtual and physical, 400 UPSs backup power systems, 2 highly virtualized server farms. So all the management systems, control systems, they are located in 2 centralized data centers, which they can provide users with the services. In general, we have 3 data centers. One data center is for like a disaster recovery, for storing video for a long time for the users. The other 2 data centers are for the servers and the control and management system. This platform can support web and mobile users. So it's one of the state-of-the-art CCTV platforms in the world. It includes integrated voice communication system with more than 900 endpoints, which most likely when you go to one of those train stations, you can see an orange box at the corner of the platform or in the middle, and that all those VoIP entities, they're integrated with the CCTV system. So the operators can not only monitor the video, they can also have a 2-way communication with people on platforms. So for the infrastructure, we are monitoring more than 15,000 entities, more than 60,000 sensors, and in general, 150,000 data channels. And all these data channels, they're in real time, so we collect data from all these data channels. Some of them are generating a high rate of data, like, for example, we monitor every single switch port on the network to monitor the throughput, the capacity, and in general, analyze the traffic which is going through the network. The platform has integration with third-party applications. For example, this platform has the capability of monitoring train-borne cameras. So the main platform is for land-based cameras, but also it has integration with trains and monitor train cameras, and plus video analytics. So if you look at the right pictures, the 3 pictures, one of them is actually a real picture from the video analytics system. You can see that some people are going through the tunnel and the system is generating an alarm. So there are different capabilities for video analytics deployed in this platform, which, for example, can help with the safety of the platforms, tunnels, or, for example, it can detect crowd on platforms, detect how many people you have, for example, for a specific area to help optimizing the traffic plan or distribution of people on platforms. On the bottom, there's another picture. You can see a large video wall with more than 100 cameras monitoring on the video wall. This is one of the control centers which is using the CCTV system to actively monitor the situation. For example, it can be used for incident response teams. Okay, now I will present 3 use cases which we use data analytics to help Sydney Trains to improve the efficiency of their operation or the cost of deploying this system. The first case is for how we can use the user activity data to reduce the CAPEX for deploying new cameras. So in general, we have different users. We have thick clients, we have mobile clients, we have web users. Every single activity of these users is monitored. Which camera they use, how long they use it, for what purpose they use it, The system is designed for up to 2,000 users. At the moment, we have more than 1,000 active users. And you can imagine how much data is generated from each one of these users. For example, at any moment, they can be monitoring like 64 cameras. So in total, we're talking about a huge amount of data generated from these users. They do different activities. For example, it can be used for station staff just for situation awareness, monitoring the platform, or it can be used by police for investigation, or it can be used for network control teams for incident responses. For example, if there's a missing person, or for example, there's a situation, for example, someone is jumping in front of a train and they want to control the situation, this monitoring platform is used for all these purposes. The goal of this plugin we developed for the CCTV system was to reduce the CAPEX for deploying new cameras. In general, the problem here is that when you want to deploy, let's say, one camera, so it's not only the cost of that one camera. In total, you need to think about the cost of the infrastructure, the cost of the servers, the storage, the labor. So the camera can be, let's say, $500, $1,000, but in total, the cost of deploying one camera can go up to $10,000, which is massive. So to help Sydney Trains to make smarter decisions, what we did, we developed some cross-platform reports for them to be able to, for example, understand between 12,000 cameras for a specific area, for example, station 1, platform 2, how many of those cameras are not used, or they're not used that much as planned before. Or it can be for the whole network, for example, or a large area, a rail train, a train rail, which you can see, for example, this is just an example of the output of the report. It tells that, okay, for example, these cameras, they are the least used cameras in the network. So what it means for Sydney Trains, it means that now they can make a decision based on this information. They can decommission these cameras and reutilize the hardware, the capacity, the infrastructure, the network to deploy new cameras or somewhere which they know that for sure that area is prone to incidents, or for example, that definitely they need more cameras to cover the area. It had a good result, and it is at the moment used by Sydney Trains to optimize the CAPEX. So this case was just a small case. There are multiple different cases of doing similar things for the operation. This was just an example. The next two cases, they're more focused on maintaining the system, how you can more efficiently maintain the system. Indra has deployed this massive network, but also Indra is maintaining the system. The challenge here is that this system is used by different users, different requirements, and everything is governed under tough SLAs, very, very strict. For example, if something goes wrong, it can be in Scone, a very far away station, and in general, we have only less than an hour to fix that issue, bring back the camera, or if, for example, a problem happens for a data center or a server, it can be, the scale of the problem can be bigger, and we have shorter time to fix it. So how we can optimize the whole maintenance operation? One of the interesting issues we always have is temperature in server rooms, in monitoring rooms. So to give you a brief idea of what's happening here is that we are monitoring more than 380 server rooms for this platform. So it's geographically massive. We are responsible for corrective maintenance. What corrective maintenance means is that, for example, if something goes wrong, then we need to fix it. So what does it mean, fixing the problem? The first one is that, for example, you have an air conditioner in the room. So you need to deal with reality. The problem is that most of those air conditioners, they don't have any monitoring or remote monitoring or control feature. They're a simple air conditioner. Anyone can go inside the room. For example, you have a technician working inside the room. They feel that it's a bit cold, so they change the temperature. And now after 2 hours, you see that the temperature is going high in the room, and you get an alarm on the system saying that, oh, in 2 minutes, everything goes down because it's too hot. It's a massive problem. So what we do for corrective maintenance, if we detect those situations, we need to do two things. We may need to fix the air conditioner, or we may need to, for example, do something more fundamental, like shifting the load from those server rooms to another server room or another location, just to make sure that when the system goes down in the room, which the temperature is high, still the network can stay up and running. So it's in the background, maybe you should mobilize like 10 people working together to make sure that by the time you get hit by that temperature issue, everything stays online, up and running. On the right side, it's just a graph as an example of what the temperature looks like when you monitor the temperature. It's a real graph from our system. You can see it goes up and down. So these are the cycles of the day, or for example, the air conditioner starts cooling down the room and then it stops, and we are monitoring all these activities. Then we get to the preventive maintenance. What's the difference between preventive and corrective maintenance? Preventive means that, for example, you do regular maintenance. You schedule a plan for your technicians, for your team. They go to these sites every 2 months, 3 months, 4 months. It depends on the likelihood of facing any issue in those rooms. And then, for example, they service the air conditioner. They check that if something's wrong, or for example, if they need to service it, clean it, some parts of the air conditioner. And also they check the components of the air conditioner to make sure that they're working in their nominal performance space. For example, on the right side, I give you another graph, just an example of real world what you can get. You can see that there was a temperature jump. It was because of a faulty unit in an air conditioner, and then someone fixed that problem, and the temperature went back to the normal average temperature you can expect from the room. Okay, now the interesting part, predictive maintenance. Okay, so we talked about corrective, which we fix an issue after it happens. We do preventive maintenance, which we explained that it means that you don't know if it happens, but you're expecting it to happen in the next, let's say, 6 months. So you do regular maintenance to decrease the likelihood of having that problem. But predictive maintenance, it's another layer on the top. It means that I'm going to monitor the status of the system. I can collect some data. And from the data, then I can, for example, create a model or do some, let's say, simple regression to understand, okay, this is the trend. And in 3 days, I may have the problem. So it gives you enough time to plan ahead, to think about how you can fix the issue. And also, the other difference is that maybe when you see the trend, still it's not an issue, and it's not going to be an issue in 2 months or 3 months, but it's decreasing the longevity of the system. So for example, let's say you have a storage system in one of these rooms. The cost of that storage system can be, let's say, up to, for example, $100,000. These are real figures. And you don't want that system to die. You know, it's very expensive. And the temperature is one of the key factors for that system to fail. If you constantly have high temperature in that room, still below the threshold, it can decrease the longevity of the system. When you see the trend, when you see that, oh, okay, so I can see that this room temperature is going up and down over 2 weeks or 3 weeks, then you can plan ahead saying that, okay, for example, I need to increase the capacity of air conditioner in that room. On the right side, I gave you just an example of, for example, what we detected in, it's from the actual systems. The bottom picture, you can see that over a week, 5-6 days, the temperature is going high. So each mountain, each peak is a day. So you have lower temperature at night, you have lower temperature in the evening, you have the highest point in the middle of the day. And then if you look at the maximum temperature, if you do a simple regression, you can see that it's going up. It's going up, and you can see that easily if it continues this trend, you will have an issue 2 days later. The temperature passes the threshold, you need to turn off all the systems. Why it happens? So there are two different trends. You can have a fast temperature rise. It can be because of a failure in the component, or it can be a human error, like what I told you. A technician goes to the room, it feels cold, then the technician turns off the air conditioner or changes the temperature. Or it can be a slow rise, like this example, which, for example, it can be because of performance degradation, or again, human error. For example, someone set a wrong set point for the air conditioner, or it can be because of weather. So the goal here is to predict those problems. The other case is very similar to the one I told you, but this one is for power systems, for auxiliary power systems like UPSs. So we are monitoring more than 400 UPSs. Everything's monitored: input voltage, current, frequency, battery condition, output. For corrective maintenance, all the components of the UPSs, they are monitored. Plus, we see it, if there's any power outage, we can detect it. For preventive maintenance, we use this data to, for example, distribute the load between different phases, or increase the efficiency of the software to control the UPS. And the interesting part, which is the predictive maintenance, this one is another project we're working on. The goal here is to, for example, for batteries. Batteries can lose their capacity over a long time. For example, in 2 years, the capacity of your phone battery can go to 60%. I think this is a common problem for everyone. It's the same case for any kind of battery. If you can detect that trend over a long time, then you can see that if the battery is fundamentally wrong, something's fundamentally wrong inside the battery, you can see if that trend, the slope is changed or not. Then you can replace those batteries on time. Or, for example, one of the other things is that not everywhere you can use a power quality system, power quality monitoring systems. So you cannot measure all the problems directly, like harmonics. One of the things we are doing is to analyze understanding the correlation between different parameters. For example, if we cannot directly monitor harmonics distortion, but we can monitor something else like voltage fluctuation, can we use that information to predict the changes in, for example, harmonics distortion? This is one of the areas we're working on. And again, the goal here is to give the maintenance team enough time to respond to problem. So they will have like months to fix it. And the other problem is that for power systems, fixing the problem, most of the time, you cannot, for example, simply go there and replace a battery or a UPS, or even if it's harmonics distortion, it may take months for you to fix it. Thank you, everyone. I know we ran out of time a bit, so if you have any question, I'm more than happy to answer.
I was saying, Milad, thank you very much.